The recording is live. Captions are on. Let's get started talking about today's topic. We have officially finished with Module Exam 1 content. We are picking up with Module Exam 2. So this is the start of Module Exam 2 content. The very first thing we're going to hit the ground running with is known as the mole concept. So the lighting's a little off. Let me just pull down this one in the back too. Yeah, that's a lot better. All right. To understand the mole, I want us all to think of $1. When you go to a gas station, when you go to Target, when you go to Walmart, Costco, wherever you go, and you purchase things in the currency of the dollar. But the dollar isn't really the only thing we can use when purchasing stuff. Hell, we can make the argument that $1 is also 4 quarters. We can make the argument that $1 is 100 pennies. We can make the argument that $1 is 10 dimes, and that $1 is also 20 nickels. These are different ways of saying the same thing, $1. But when we go to the gas station and I ask for a bottle of water, the gas station attendant does not say, hey, it's going to cost you 6 quarters. He doesn't say it's going to cost you 150 pennies. He doesn't say it's going to cost you 22, 25 nickels, if I remember correctly, if I did that math correctly. What does he say? He says it's $1.50. Why do we use $1? Why don't we use quarters, pennies, and dimes or nickels in our casual day-to-day conversation? Anyone want to take a guess? It's a really easy answer.
It's the simplest way.
It's the simplest way to describe currency in a way that everyone understands. Sure, there are some contexts. If you've ever been to a laundromat, they probably say, yeah, it's 3 quarters. That's based on the context. But pretty much everyone uses the dollar to understand what we're talking about currency. But that $1 also means 4 different things: quarters, pennies, nickels, and dimes. In the same way, I want you to think about the mole. The mole, that word right there, mole, can be thought of as chemical currency. The mole represents the simplest way for us to describe various quantitative features about chemicals. It can mean many things, just like $1 means 4 quarters, 100 pennies, 10 dimes, 20 nickels. A mole can mean many, many things, but we use mole because it's the simplest way to describe chemical currency. So now, what exactly can we equate a mole to? Well, 1 mole of anything is equal to 6.023 times 10 to the 23 of anything. This term, this number right here, 6.023 times 10 to the 23, is known as Avogadro's number. Not to be confused with avocado. Avogadro is the guy who quantified it. He was the very first person to say 1 mole is 6.023 times 10 to the 23 of anything. As we further applied it to chemicals, for example, oxygen, 1 mole of oxygen is equal to 6.023 times 10 to the 23 atoms of oxygen. So instead of us consistently saying things to the 10 to the 23, we just say 1 mole. We can also say that 1 mole of a chemical compound, or just of a chemical, is equal to that chemical's atomic or molecular mass. Now notice I'm using two terms here. I'm using that word atomic and I'm using that word molecular. I want to take a second just to talk about the difference between the two. When we're dealing with something that is a single atom, aka in this case fluorine, so just fluorine, even though there's two of them, it's just fluorine. We use the word atomic to describe it. It's just one element, so it's all one atom, so we say atomic. Compared to something like H2O, water, water is a combination of different atoms. We use the term molecular to describe it. So just as we said 1 mole of oxygen, just a single element, is 6.023 times 10 to the 23 atoms, we can similarly say that 1 mole of H2O is equal to 6.023 times 10 to the 23 molecules of water. Where use of that word molecules refers to the fact that we're dealing with a molecule, a combination of multiple atoms, versus atomic or atoms when we're only dealing with one atom of its kind. So the use of atoms versus molecular is really just a context thing. They don't mean two completely different things. It's just about the context we're speaking of. Now, I just said that 1 mole of any chemical is equal to its atomic or molecular mass. I'll give you your exam at the end. What exactly does that mean? Well, let's look at water. 1 mole of H2O is equal to its molecular mass. So how do we get the molecular mass of H2O? Well, that's easy. We know that there are 2 hydrogens. There is 1 oxygen, H2O. We know that hydrogen, according to the periodic table, has a mass of 1. And we know that oxygen, according to the periodic table, has a mass of 16 when rounded. This is what tells us that 1 mole of water is equal to 18 grams per mole. That is 1 mole of water. But just 1 page ago, I also said that 1 mole of water is 6.023 times 10 to the 23 molecules of water. Keep thinking back to that analogy, the chemical currency. $1 can mean many, many things. 1 mole can mean many, many things. But we use the mole just as we use the dollar, as Ryla pointed out. It's the easiest, most convenient way of describing things. So what is the direct implication of these statements right here? Well, let's think back to a little bit of math, for instance. If A is equal to B, and A is also equal to C, then by the law of math, we know that B is equal to C. We can use this logic right here to equate the two, such that we're able to say that 18 grams per mole of water contains 6.023 times 10 to the 23 molecules of water. This is what leads to the general statement that the atomic or molecular mass is equal to 1 mole, and that 1 mole is also equal to 6.023 times 10 to the 23 atoms or molecules. This relationship is incredibly fundamental to understanding chemistry, because not only does it give us a convenient way to describe these things, a mole, but we're also able to relate mass to the number of molecules or atoms. In other words, within 18 grams of water, there is times 10 to the 23 molecules. Here's how we can use this in this class and subsequent calculations. We get two new formulae. N is equal to M over MM. I will define them in just a bit. N is equal to M over MM. And then N is equal to capital N over N subscript A. The letter N refers to the number of moles of a substance. Lowercase m is the mass of the sample. MM is the molar mass. It's that atomic or molecular mass. N sub A is 6.023 times 10 to the 23. That's Avogadro's number. That's where the A comes from. And then the capital N on top is the number of atoms or molecules, depending on the chemical we're talking about. These two new formula represent our next big module, which is focused on chemical calculations. If you haven't bought a calculator yet, now would be the time. Because now we're going to actually start using these formulae in a question. Everyone should have a copy of the in-class problem set in front of them. Is there anyone who does not have a copy? See one hand. Is there anyone else who does not have a copy? Bigger. Like that? Okay. So now I'm going to do a question or two from this document. Let me just bring it up on my end. New problem set means new questions to do, new worksheet, new extra credit. I'll talk about the extra credit once I'm done. I would like to do one of the questions on page 2. I'm going to do page 2, part F. All right, let's take that screenshot. And let's solve it. Before we begin, I'll just remind ourselves of the big formula that we may be using. N equal M over MM, or N is equal to capital N over N sub A. And the first question we're doing is page 2, part F. How much does 1.4 moles of aluminum phosphate weigh? All right, let's talk about this question. Ultimately, it's asking for how much does it weigh. So we're looking for mass. Based on the question, we're given N. Both of these together tell us we will most likely be using the formula on the left. We're given N. We're being asked for lowercase m. The only thing missing, of course, is that capital MM, molar mass. Don't worry, though, because we can calculate it. So we'll be using N equal M over MM. We know that N is equal to 1.4. That was told to us in the question. And we know that lowercase m is what we're trying to find. Right now, what we need to do is calculate the molar mass of aluminum phosphate, which we can get by summing the masses of all the elements present. We see that there is an aluminum, we see that there is a phosphorus, and we see that there are 4 oxygens. We want the total mass of this compound. I'm only going to round numbers here. If you have your periodic table, you can find the numbers. The molar mass of aluminum is 27. The molar mass of phosphorus is 31. The molar mass of oxygen is 16, of which there are 4 of them. Put this in your calculator, you get a whopping 122 grams per mole. Now that we have all the pieces, we can plug them in. 1.4 is equal to the mass divided by the molar mass, 122. Really testing our algebra skills here. How do we get rid of this? How do we make this make sense? We multiply both sides by 122. In doing so, we cancel out the fraction. What we're left with is M is equal to 1.4 times 122. We put this into our calculator, we get 170.8 grams. I could ask you on an exam to write these to a certain number of significant figures. Does anyone have any questions on part F? Yes. Yeah, generally you round to whole numbers just because of simplicity. When you get to that point of decimals, it really doesn't matter. But there are times where on an exam, I might write the instructions, please write to how many ever decimal places, which point you would have to reflect that. I see a hand in front. I think it's Alexia. Yeah.
Is it oxygen
or
or?
4-1. Where do you have 4-1? 4-0. The 0 is an O. It's an oxygen. Don't forget, I write my zeros with a line right through it. So that's just an O as in oxygen. Thank you for asking. Any other questions on this? Okay. I would now like to do part C. Whoops. Let me just take a screenshot. All right. So next up is part C. How many grams are in that many molecules? All right, so we know ultimately that the question is asking for M, grams. We're told how many molecules there are. Why did we use the word molecules? Why not atoms? Anyone take a guess? Yes, Ryla, why? Because it's not a single element. It's hydrogen and oxygen. So the word molecules reflects that. Okay, now we have a situation where we have M and N. Technically speaking, there is no single equation that relates the two. We're trying to find M, and we're given N. Don't worry, though, because we can say that if N is equal to M over MM, and N is equal to N over N sub A, through the power invested in me by the gods of math, I can say M over MM is equal to N over N sub A. I can simply equate them to one another. In so doing, I now have a single equation that relates mass and number of molecules. All I need, of course, is the molar mass and Avogadro's number. So taking a second, we're trying to find the molar mass of H2O2. We know that there are 2 hydrogens and there are 2 oxygens. Remember, that's an O, not a 0. Hydrogen has a mass of 1. Oxygen has a mass of 16. We have a whopping total of 34 grams per mole. We know from the question that the number of molecules is 1.03 times 10 to the 23. We know Avogadro's number, that's a constant, 6.023 times 10 to the 23. So all that's left is to plug in everything and solve for M. This becomes M over 34 is equal to 1.03 times 10 to the 23. Whoops. All over 6.023 times 10 to the 23. We're trying to solve for M. So to get rid of that 34 on the bottom, we're going to multiply both sides by 34. In doing so, we cancel out the 34 on the left-hand side. So what we're left with is M is equal to 1.03 times 10 to the 23 all over 6.023 times 10 to the 23. All of that multiplied by 34. Calculators can be our best friend and simultaneously our worst enemy. Be sure that you've typed this into your calculator correctly. Let me show you what it should look like. On top, we have 1.03 times 10 raised to the 23. On the bottom, we have 6.023 times 10 raised to the 23. All of that multiplied by 34. We get an answer of approximately 5.81 grams. When instructions aren't specified, it is common practice to round to 2 decimal places. Meaning nowhere in this question did I specify anything about significant figures or the like. So just for simplicity, we will leave our final answer to 2 decimal places. So when in doubt, round to 2 decimal places. So because it's the same number right here, I'll just write it. M is equal to 5.81 grams. I see a hand in front. It's in the question. So the thing I want you to remember when using these formulae is that you are able to calculate the molar mass yourself. Meaning you will not see in the question as something that explicitly says MM is equal to whatever. This is something you can calculate yourself as long as you have the formula. And A is a constant, Avogadro's number. So you are expected to memorize that number. So traditionally, you'll be asked to either solve for or calculate mass or number of atoms or molecules. So learning how to manipulate these equations, learning how to manipulate the algebraic expressions is a skill we're going to try to develop and learn. Do we have any questions before I move on? Okay. Continuing our discussion of the mole, one term that becomes very useful to understand is percent composition. And the easiest way for me to describe to you what percent composition is to tell you the formula first. Percent composition is equal to the mass of an element all over the molar mass of the compound the element is in times 100. And of course, the times 100 comes from the fact that this is a percentage. In other words, I could ask you the question in the molecule H2O, what is the percent composition of hydrogen? How much of that molecule is hydrogen? That's effectively what I'm asking. So what would a question look like? What is the percent composition of each element in C2H5OH? So each element, and I've given you the full formula. Arbitrarily, I'm just going to work from left to right. So starting with carbon, I can see in the molecule, there are 2 carbons. So on top, I will have 2 times the mass of carbon, 2 times 12. All over the molar mass of the compound. Well, that number is not readily available to us in the question. No big deal, though. We can calculate it. The molar mass of C2H5OH is equal to 3 carbons added to 6 oxygens. Notice that there are in total 6 hydrogens. Whoops. And only 1 oxygen. 3 times 12, 6 times 1, and 16 for a whopping 46 grams per mole. Now that we have the molar mass, we can plug it into our formula. 46 times 100. Monica, I see your hand. I'll be there in a second. You plug this into your calculator, you get approximately 52%. Percentages are traditionally rounded to the nearest whole number? Monica, what was your question? Oh, did I make another mistake? I did make another mistake. So it should be 2 carbons. Oh, that's actually a very good. Oh my God, I completely forgot about this. Afternoon lab. Do you remember what happened last lab, the afternoon section? I was just caught making a mistake in class. That's the new policy. If I make a mistake in class and a student catches it, I will give everyone 1 extra credit on the next exam. Monica just caught my mistake. Fair warning, sometimes I say mistakes on purpose to catch you up, but that was an earnest mistake that Monica just caught. So I'm going to make a note right here. +1 EC to everyone on exam 2. I'll just make a note of it myself. Thank you for catching that, Monica. Let me just make sure that everything else looks good. 2 carbons, 2 times 12 is 24, plus 6, 30, plus 16, 46. So it was just the 2 that was wrong. The overall answer, 46, was correct. All right. So that's how we calculate the percent composition of the carbon. Copying this over so that I can keep referring back to it. After carbon, we have hydrogen, of which there are 6. 6 times 1 is 6. We already have the molar mass, 46 times 100. Put this in our calculator, we get 13%. Remember that percentages are traditionally rounded to the nearest whole number. After hydrogen, we have oxygen. There's only 1 of them, so 16 over 46 times 100. All of that is equal to 35%. And obviously what you should notice is that all of the percentages added together should give you basically 100. Do we have any questions on percent composition? Yeah, I see a hand in the back first, Alexia.
Is there a specific reason why there's 5 hydrogen and 1 hydrogen?
So the ultimate reason why it's written that way is something you will learn in organic chemistry. So it's not up to our concern right now. You are absolutely correct that you could write this C2H6O. It would be the same thing. But there are rules in OChem that prevent that. You are not responsible for that. So this is not something you'd be tested on, but rather just accept that this is the way it is. Good question. Alexia, what was yours?
Why do you put 6 hydrogens instead of 5 for a C%?
So there are 5 hydrogens here and 1 right here for a total of 6. Any other questions? Now, percent composition is not in and of itself a very tough topic. You probably notice on the worksheet, I don't really have any questions about percent composition. But what percent composition eventually leads us to is our next big topic today. Empirical and molecular formulae. The empirical formulae of a molecule, henceforth I will abbreviate it as EF. The empirical formula is the simplest whole number ratio of atoms in a molecule. In contrast, the molecular formula henceforth written as MF, is the exact whole number ratio. What exactly does this look like? Well, let's take a look at a couple examples. Comparing molecular formula to empirical formula. If we were to start with a simple one, C6H12O6, maybe our bio majors in here might recognize this compound. This is actually what's known as glucose. It's irrelevant to this class discussion, but just so you know, it is glucose. The molecular formula is the exact whole number ratio. There are 6 carbons, 12 oxygens, and 6 oxygens. The empirical formula is the simplest whole number ratio, aka we simplify to CH2O. We can see that although the molecular formula is different from the empirical, they both tell us the same thing. For every 1 carbon, there are 2 hydrogens. For every 1 carbon, there is 1 oxygen, exactly represented here. Now, the reason why this becomes so useful is because as more molecules are discovered, synthesized, made, such as C3H6O3, although a completely different molecule, C3H6O3, its empirical formula is also CH2O. And here's the overall implication of this. If they share a similar empirical formula, then they have overlapping characteristics. In other words, they belong to the same family. In other words, since we know that C6H6 is glucose, a type of sugar, an energy source, we can make the argument C3H6 is also some type of sugar. So being able to identify the empirical formula is incredibly useful because it allows us to make predictions without actually having to test anything. There are occasions, however, such as H2O, where the molecular formula is as simplified as it can get. You can't simplify H2O anymore. So its molecular formula is H2O, and its empirical formula is also H2O. Here's what this tells us, though. If the molecule H4O2 was ever discovered, in theory, it should share some characteristics with water. Same thing with H6O3, H8O4, and so on. The benefit of the empirical formula is it allows us to create families of chemical compounds. And families have a lot of traits in common. How do we calculate empirical formula? Sure. This is always a, okay, right. Yeah, I forgot. Yeah. So now that we know this, how do we calculate empirical formulae? All right, let's take a look at what a question might look like. What is the empirical formula of a molecule that consists of 78.14% carbon, 9% hydrogen, and 12.86% oxygen. You should recognize what these percentages mean. We just talked about percent composition. Here's how it becomes very useful in our questions. Here's what we're going to do. We're going to draw a table with 8 rows and 4 columns. The first column will be a blank, and then the other columns will be the atoms in question, C, H, and O, arbitrarily written in the order that was provided to us. Here's what we're going to do. Here's the process. The very first thing we're going to do is we're going to note down the percentages. Well, that's straight from the question, actually. There's 78.14% carbon, 9% hydrogen, and 12.86% oxygen. Now, if you add all of these numbers together, to no one's surprise, we do get a perfect 100%. With that, we can then assume that the total mass is 100 grams. If we make this assumption, we can then assume the masses of the individual atoms. If the total mass is assumed to be 100 and 78.14% of it is carbon, then we can assume that the assumed mass is 78.14. We can do the same thing for the hydrogen. We can do the same thing for the oxygen. So these 2 first rows are the easiest to fill out. The percentages come from the question, and the assumed mass is in fact the same number. Once we get the assumed mass, we can calculate the number of moles of each element. We know the formula, N is equal to M over MM. The mass is 78.14. The molar mass is 12. For hydrogen, the mass is 9 and the molar mass is 1. For oxygen, the mass is 12.86 and the molar mass is 16. If we put these numbers into our calculator in order from left to right, 78.14 divided by 12 is approximately 6.5. 9 divided by 1 is just 9. 12.86 divided by 16 is 0.80. And once we get the number of moles, we will then divide all numbers above by the lowest. So of the 3 numbers, 6.5, 9, and 0.8, the lowest one should be immediately jumping out to you. The 0.8. That's what then gives us our ratio. So it will be 6.5 divided by 0.8, 9 divided by 0.8, and then 0.8 divided by 0.8. 6.5 divided by 0.8 is approximately 8.13. 9 divided by 0.8 is approximately 11.3. And of course, any number divided by itself, let me just make the color right, 11.3. And any number divided by itself is just 1. This is what overall tells us that the empirical formula is C8, H11, O. Remember, by definition, empirical formula is the lowest whole number ratio. So we would not write 8.13 or 11.3. We would round it to 8 and 11, respectively. This chart right here breaks down the complete procedure to solving empirical formula questions. As the only thing will change is what's in the columns, the numbers, but these guys over here stay consistent. Let's try another one for good measure. We're going to do, is there one question on this? Yeah. From the in-class problem set, I'm going to do part, let's see which one I want to do. Yeah, let's do part A. The question says the percent composition of a compound was found to be 63.5% silver, 8.2% nitrogen, and 28.3% oxygen. Determine the compound's empirical formula. So as I said, we're going to draw that table. The atoms in question are silver, nitrogen, and oxygen. The very first part is the percentage. That is from the question. Silver is 63.5. Actually, this is getting really cramped. Let me just make it a little bit bigger. Yeah, that's better. Nitrogen is 8.2. Again, this is from the question. And oxygen is 28.3. Of course, we notice that the percentages do add up to a 100. So we can quickly say the mass is 63.5, 8.2, and then 28.3. After the mass, we can calculate the number of moles. So we're going to need the periodic table, if I remember correctly. Silver is 107. Nitrogen is 14. Oxygen is 16. If we put these numbers in our calculator, 63.5 divided by 107 is 0.59. .2 divided by 14 is also 0.59. I I do see your hand, Paul. I'll get to you in a second. And then finally, 28.3 divided by 16 is 1.77. Paul, I'll take your question. Okay. That shouldn't really affect our answer too much, but let's just do that for Paul's sake. 63.5 divided by 108. Change it to 108, it's still 0.59, so it doesn't really change our answer too much. Now that we have the moles, we will then calculate the ratio, which is we have to divide all of the numbers above by the lowest. Recognize in this case, there are two numbers that are identical that are both the lowest. Doesn't matter which one you pick, of course. 0.59 divided by 0.59 is 1. 0.59 divided by 0.59 is also 1. 1.77 divided by 0.59. Let's get the exact number. 1.77. Whoops. Divided by 0.59. That's actually a flat 3. This is what tells us that our empirical formula is AG1. We don't traditionally write the 1. N1 and O3. Now, a very common question that comes up is, do we have to write it in a specific order? Does the silver have to come first? No. You could have written NO3AG, O3AGN, any order you want. The point of the question is to get the empirical formula. I don't care about the order. Does anyone have any questions on anything we've done so far? Okay. I would like to do another question. It's not on the problem set. I'll write it out right here. A gasoline additive consists of 72% chlorine, 23% carbon, and 5% hydrogen. The question first asks, what is its EF? What is its empirical formula? The question doesn't stop there. It then says, if the if the molar mass of the additive is known to be 100 grams per mole, what is its molecular formula? So technically, two questions we're doing here. Let's go in order. The first thing we're going to do is we're going to calculate the empirical formulae. To get that, we're going to draw our table. We're dealing with chlorine, carbon, and hydrogen. Again, just written in the order that the question gave me. There's no correct order. The very first thing is the percentages. That's straight from the question. 72, 23, and 5. We can then assume the mass to be the exact same, 72, 23, and 5. then we can get the number of moles. Chlorine is 72 divided by 36. Carbon is 23 divided by 12. Hydrogen is 5 divided by 1. We're then going to calculate these things. 72 divided by 36 is a flat 2. Excuse me. 23 divided by 12 is 1.92. Sorry that it's getting kind of scrunched up. I'll zoom in a little bit more. 5 divided by 1 is 5. We will then identify the lowest number, which should arguably be the 1.92. And then we're going to calculate the ratio. Two divided by 1.92, 1.92 divided by 1.92, and then 5 divided by 1.92. 2 divided by 1.92 is approximately 1.04. Any number divided by itself is 1. And then 5 divided by 1.92 is 2.60. This is what tells me the empirical formula is Cl1, C1, H2. Now that 2, a 2 should bother you. Everyone's quick to try to correct a mistake now. What's up? Is it a 2 that you're talking about? Yeah, that's exactly what I'm coming to. I wrote 2, yet by all mathematical intents and purposes, 2.6 should be rounded to 3. We do not round in this way for empirical formula. The simple reason is it's easier to underestimate than overestimate. Why? Because you're talking about actual compounds. If you rounded this up to 3, you are claiming that there is 0.4 more than there actually is. So it's easier to round to 2. That way you can say confidently, there is at least 1 chlorine, there is at least 1 carbon, there is at least 2 hydrogens. So the big rule about empirical formulae is you only round up if it's 0.9 or higher. That's the big rule about this stuff. And really, what I think might help you guys understand this is kind of the basic idea behind forensic science. If you've ever watched any of those CSI, NCIS, I guess nowadays it's like 911 on Fox and all that stuff, any of those forensic scientists, this is what they do. They take a sample from the crime scene, they have fancy equipment, and the equipment spits out the percentages. They take a sample of the gasoline additive, they run it through their machine. The machine tells them 72% chlorine, 23 carbon, 5 hydrogen. They then carry out these calculations themselves. They probably have a calculator. And then from there, they're able to say, hey, that gasoline additive that you found at the crime scene, that's actually ClCH2. And hopefully when thinking about it in the context of a crime scene investigation, it makes more sense why we would prefer to underestimate than over. Because if we overestimate and we're wrong, well, whoever killed that person got off. So it's easier to underestimate. So the rule is we only round up if 0.9 or higher. Here's what that means for you as a student. It is on me as your instructor to make it absolutely clear in a question like this, will I round up or round down? Meaning, if you do your calculations and you get, I don't know, 1.87, do you round up or round down? Down. If you get 1.91, do you round up or round down? Up. So it's on me as your instructor to ensure any question I give you, there is no ambiguity. But the rule is only round up if 0.9 or higher. That's the empirical formula question, part A. Now let's do part B, where it says, if the molar mass of the additive is known to be 100, what is its molecular formula? There is an equation for that. Molecular formula, MF, is equal to the molar mass of the sample divided by the molar mass of the empirical formula multiplied by the empirical formula. We're trying to find MF, okay? We already know the empirical formula, and we know the molar mass of the sample. That was told to us in the question. If the molar mass of the additive is known to be 100, so all that's missing right now is the molar mass of the empirical formula. Have no fear, though. We can calculate that pretty easily. The molar mass of the empirical formula, we recognize that there is 1 chlorine, 1 carbon, and 2 hydrogens. Chlorine is 36. Carbon is 12. Each hydrogen is 1. So 2 hydrogens is 2. For a whopping total of 50 grams. We can then plug this into our equation. The molar mass of the sample that was told to us in the question, that's 100. The molar mass of the empirical formula, we just calculated that. That's 50. And then the empirical formula itself is ClCH2. Shouldn't need a calculator for this. 100 divided by 50 is 2. So it's 2 times ClCH2. That's what tells us our final answer is going to be Cl2, C2, H4. The molecular formula is the exact whole number ratio. Cl2, C2, H4. The empirical formula is the simplest whole number ratio. For every 1 chlorine, there is 1 carbon, there are 2 hydrogens. Does anyone have any questions? All right, here's your assigned extra credit. Your extra credit will be all of page 4. All of page 4, so that's 3 questions. You have the space to write it. And any 10 questions from page 2. Any 10 questions from page 2 and all of page 4. Everything else is for your own practice. Please notice that the very first page says, from the name, give me the formula, then the mass. So this is additional practice for nomenclature, since as you can imagine, it comes in really handy here. We'll end lecture for today. If anyone has any questions, come talk to me after class. If not, what day is it today? Thursday? I'll see you all tomorrow. We have a wet lab tomorrow, so please come dressed appropriately. I'll see you then.